Welcome. The notation for average rate of change is usually written delta y over delta x to represent the change in the function value at each end over the change in interval length. For a function f of x over the interval a to b, you may find average rate of change by calculating the function value at each endpoint value, a and b, over the length of the interval, which is b minus a. Example, consider the function given. We're going to find its average rate of change over the interval, then find its instantaneous rates of change at each endpoint, at the endpoints of each interval. Let f of x be equal to x to the 3/2 power over the interval 9/16. The function value at each number in the interval endpoint, we're going to calculate f of 9. 9 to the 3/2 is square root of 9, which is 3 cubed, that's 27. The other endpoint, 16, we substitute into the function f of 16, which is 16 to the 3/2 power. Square root of 16 is 4. 4 cubed is 64. So to calculate the average rate of change, the delta y, which is the difference in your function values, 64 minus 27, that's 37, divided by the interval length. How far is it from 9 to 16? 7 units. Very good. So your function change compared to your interval length is 37/7. In blue, I have drawn a line that goes through the function at 9 and 27. Recall that a point on a curve is the input and output paired up. So at 9, we had a function value of 27. 9/27's on the graph. We subbed in 16. We got 64. So 16/64 is another point on the graph. When you draw a secant line through those 2 points, the slope of that secant line is 37/7. The instantaneous rate of change at the endpoints is calculated by taking the first derivative of the function and individually substituting the values of the endpoints. Well, our first derivative, since we started with x to the 3/2, our first derivative is going to be 3/2 x to the 1/2. X to the 1/2 can be translated back to square root of x. When we substitute in our left endpoint of 9 into the first derivative, 3/2 times the square root of 9, well, square root of 9 is 3, times 3 is 9/2. So that's the slope of the tangent line of our function at the x value 9. This red line on the graph up here at your top right, that's the tangent line to the original function when x is 9. It has a slope of 9/2. That's the instantaneous rate of change. The other endpoint in our interval was 16. F prime of 16, that's 3/2 times the square root of 16. 3/2 times 4 is 6. So this other tangent line at the top right of your screen is the instantaneous rate of change when x is 16. And so that rate of change is 6. Consider the function given. Find its average rate of change over the interval, then its instantaneous rates of change at the endpoints of the interval. So we're going to take the function x cubed minus 2, and we're going to investigate it over the interval -2 to 2. So we start, and we're only going to consider an x value of -2 to +2. That's the interval. This is the function x cubed minus 2. When we sub in our left endpoint in the original function, -2 cubed is -8. minus 2 is negative 10. So that gives us the point negative 2, negative 10 as a point on the function, on its graph. The right endpoint 2 cubed is 8, minus 2 is 6. So that tells us the point 2, 6 is also on the graph of the function. If we cut through the graph secant, at those 2 points, we get this blue line. Let's find its slope. The function values change from 6 to negative 10. That has a distance of 16 units. The interval length from negative 2 to 2, that's 4 units long. So we have a vertical change of 16 over a horizontal change of 4 for an average rate of change of 4. That's the slope of this blue line. Now when we take the derivative of our function, we're going to get 3x squared. Negative 2 is a constant, so it goes to 0. Our first derivative being 3x squared, and that's down here. When we investigate it at the interval endpoints, we're going to check it at negative 2. Our first derivative at negative 2, negative 2 squared is 4, times 3 is 12. And then the other endpoint, positive 2, 2 squared is 4, times 3 is 12. When we go up here to the graph, the red lines are the ones that I use to indicate the instantaneous rates of change at negative 2 and positive 2. Tangent line is touch, and those both have a slope of 12. Secant line, secans meaning cut, we cut through the graph at 2 points, while tangent touches at 1 point. The graph shows the estimated number of milligrams of a pain medication, M, in the bloodstream T hours after a 1,000 milligram dose of the drug has been given. So we have a graph that shows the concentration of the medication in the bloodstream over T hours. By the look of the graph, the medicine has completely gone out of the body after 6 hours. We're asked to estimate the average rate of change of the milligrams per hour over the interval from 5 to 6. Well, the medicine is leaving the body between 5 and 6 hours. We're going to find out how much on average it's leaving. Well, at 5, there appears to be 600 milligrams of medication in the body. So we have the intersection, 5 hours and 600 milligrams. That gives us 1 point to work with. At 6 hours, the medication has totally left the body. So at 6 hours, there's no medication remaining in the body. The change is 600 milligrams, but it's negative because the medication is leaving the body. So 0 minus 600 is negative 600 milligrams in a 1 hour interval. So the average rate of change of medicine in milligrams per hour over the interval 5 to 6 is negative 600 milligrams per hour. Over what interval is the average rate of change approximately equal to the rate of change at t equals 3 3/4 hour? So let me zoom in a little bit, or zoom out. I took a tangent line and marked at what I thought was about 3 3/4 hours. That tangent line appears to be pretty flat. If that's truly the peak of the medication in the bloodstream, then you expect a horizontal tangent line because the medicine builds, peaks, and then it goes out of the bloodstream. These intervals at the bottom you'll be given in your WebAssign course, and what you do is, like if you take 3 to 6, you would take the function value at 3, the function value at 6, draw a secant line through those two. If that has the same slope as this one, you would choose that interval. The only interval I could find that had a pretty close to a horizontal tangent line, or at least one that looked a lot like this one, was from 2.25 to 5. At 2.25 hours, which would be 2 hours and 15 minutes, there's approximately 600 milligrams in the bloodstream. At 5 hours into the medication being in your body, it appeared there was also another 600 milligrams of the medicine, which would give a secant line that matched the same slope as this tangent line. Let P equal total profit, R equal total revenue, and C equal total cost. Marginal profit, revenue, and cost are the rates of change of each category with respect to units produced or sold. When you see marginal profit, we're looking at the instantaneous rate of change of profit per unit sold or produced. dr over dx, that's marginal revenue. dc over dx is marginal cost. These are all first derivatives. This page is just strictly an introduction to the terminology. We already know how to do first derivatives. Find the marginal cost in dollars for producing X units. Our cost function is 275,000 plus 9,200X. The change in cost over change in producing X units would be our first derivative. This constant has a derivative of 0. This linear term has a derivative of 9,200. So our marginal cost is $9,200 per unit. The marginal revenue in dollars for producing X units, we have a revenue function given. That's 23x minus x squared. The change in revenue for producing X units is 23 minus 2x, the first derivative. Our notation you can either leave as dr dx or you can just call it r prime. The main thing is to realize you're taking the first derivative. And then finally, find the marginal profit in dollars for producing X units when profit is negative 0.35x squared plus 6,000x minus 1,050,000. The derivative of our first term, negative 0.35 times 2, is negative 0.7 or 70x, because you only take one off your power, plus 6,000. And that's a constant, so it has no derivative. I mean, it's 0, but we don't have to write it. I hope this video helps out. Reach out to me by email, phone, or ask questions in class, and I'll do my best to help you out.